Hello and welcome. Have you ever wondered what really happens when you write a simple line of code? Today, we are going on an incredible journey, a real deep dive. We're going to trace one single operation, following it from your Python editor, down through the complex layers of an AI framework, all the way to the bare metal, the silicon itself.
And this is where it all starts. C equals A plus B. I mean, it looks so simple, right? It's clean, it's intuitive, it almost feels like magic. But let me tell you, behind this beautiful, simple line of code, there is a whole world of complexity. It's a carefully choreographed dance between software layers, and it's all designed for one thing: unbelievable speed.
So, you hit run. What's the very next step? How does the computer take this high-level idea of adding two tensors and turn it into a blisteringly fast calculation on a GPU? That's the exact mystery we're going to unravel together today.
So here's our roadmap for the journey. We'll start by crossing the language barrier from Python into C++. Then we're going to meet something called the dispatcher. Think of it as the framework's traffic controller. After that, we'll see why we need compilers to get even more speed, what trips them up, and finally, how it all becomes raw instructions that the hardware can actually understand. Okay, first stop on our journey. We're leaving the comfortable, friendly world of Python and heading into the high-performance engine room of the framework, which is all written in C++. You know, we all love Python because it's so flexible and easy to use. It's built for us, for humans. But when you need to squeeze every last drop of performance out of your hardware, you've got to get closer to the metal. And that means using a language like C++. So our simple Python operation has to be translated into something that the C++ backend, in this case A10, can actually execute with maximum efficiency. And check this out. This isn't just a simple one-to-one translation. A Python tensor object gets completely transformed into a much more detailed C++ structure. Look at the memory, for instance. Python uses a general-purpose garbage collector, which is fine, but for heavy-duty AI work, it's slow. The C++ side uses a specialized allocator that's designed to handle and reuse huge chunks of memory incredibly fast. It's all about adding the crucial details the hardware needs.
So this new C++ object is now packed with essential metadata: the shape, the data type, which device it's on, and this one's super important, the stride. Think of stride like a map. If your tensor is a big 2D image, it's actually stored in one long 1D line of memory. Stride tells the computer exactly how many steps to jump in that line to get from one pixel to the pixel directly below it. Without that map, fast math would be impossible.
All right, so our operation is now speaking the language of C++. It arrives at this critical crossroads, this decision point, called the dispatcher. Its whole job is to figure out which exact piece of code is going to run our addition.
The dispatcher is honestly one of the most brilliant parts of PyTorch. See, for an operation like torch.add, there isn't just one function. There's a version for the CPU, another one for CUDA GPUs, a different one for handling autograd. You get the idea. The dispatcher is the traffic controller that looks at the operation and its inputs and routes it to the perfect implementation. These little implementations are often called kernels. They're just tiny, hyper-optimized programs for a specific task on specific hardware.
And this table here visualizes it perfectly. It's basically a giant lookup table. The operator, say torch.add, is the row. The context, like is this on a CPU or is autograd turned on, decides the column. The dispatcher just finds the right cell in the grid and boom, it calls the function that's waiting there.
So that's the million-dollar question, right? This decision has to be lightning fast and 100% correct every single time. How does it figure out the exact context for our operation? Well, it does this by building what's called a dispatch key set. It's a step-by-step process. First, it looks at the tensors themselves. Are they CUDA tensors? Okay, add the CUDA key. Then it checks the environment, the thread local state. Are we training? So autograd is on? Add the autograd key. It gathers up all these clues, finds the one with the highest priority, and that's the path our operation takes. It's a really clever system.
So, we found the right C++ kernel. It's fast, but here's the thing. Calling these kernels one by one from Python creates a bottleneck. To get truly mind-blowing performance, we need to zoom out and see the bigger picture. We need a compiler.
By default, PyTorch runs in what's called eager mode. It does one operation, then the next, one at a time. It's fantastic for debugging, but it's not the fastest way. Compiled execution, on the other hand, looks at a whole chunk of your model at once. It can see you're doing a multiplication, then an addition, and can be smart enough to fuse them into a single, super efficient operation, which cuts down on overhead big time.
And this is where the magic of torch.compile comes in. It's the tool that takes your dynamic, flexible Python function and transforms it into a static, analyzable computation graph. This graph is like a blueprint of your code, and it gives the compiler that global view it needs to do its optimization magic.
This graph is called an FX graph. You can think of it as a pure data flow diagram. It's not Python code anymore. It's what's called an intermediate representation, or IR. This is a classic compiler strategy. It creates this perfect in-between language that's not tied to any specific hardware, which makes it way easier to analyze and optimize before generating the final code. This IR is the key that unlocks all the powerful back-end compilers. Now, the power of torch.compile is all about capturing these big, unbroken graphs. But not all Python code plays nicely. Sometimes the compiler just hits a wall it can't get past. And this isn't some minor detail, it's a really big deal. As this quote from a research paper points out, graph breaks are one of the biggest enemies of performance. When a break happens, you lose all the benefits of compilation for that little piece of code and fall right back to the slow, one-at-a-time eager mode.
So what exactly is a graph break? Imagine a UN translator who's flawlessly translating a speech, but then the speaker uses a really obscure slang term. The translator has to stop, say, "I don't know that one," let the original speaker say it, and then try to pick up where they left off. It works, but it completely breaks the flow and slows everything down. That's a graph break.
And here are some classic examples. A normal Python if statement that depends on the value inside a tensor is the #1 cause. Why? Because the compiler analyzes the code before it runs, so it has no idea if that sum is going to be greater than 0 or not. It can't predict the future. A static graph needs to know the exact path beforehand. Same thing with printing a tensor. That's I/O, and a computation graph has no idea what to do with that. The trick is to rewrite these using graph-friendly tools like torch.ware.
All right, we're on the home stretch. We have our optimized FX graph. Now for the final step, turning that graph into actual instructions the hardware can run. This is where the rubber really meets the road. This is known as the lowering process. It's like going from a high-level architectural blueprint of a house down to the detailed electrical wiring diagram. Our abstract FX graph gets lowered into a more specific, low-level IR. For GPUs, that's often something called Triton IR, and then finally, that low-level IR gets compiled into the actual machine code for the GPU or CPU.
And even here, at the very last second, the compiler is still working its magic. It's fusing operations to reduce memory traffic, it's meticulously planning memory layouts, it's tiling loops to make sure everything fits in the superfast cache, and it's vectorizing code to use powerful instructions that can process tons of data in a single clock cycle. It's squeezing out every last drop of performance.
And that's our journey, all the way from a simple C equals A plus B to a hyper-optimized stream of machine code executing on silicon. But it does leave us with a fascinating question, doesn't it? As we get more and more specialized hardware, TPUs, all kinds of custom AI accelerators, is this journey from Python to silicon going to get even more complex? Keeping up with that hardware explosion is one of the biggest challenges facing the field of AI today. Thanks for coming along on this deep dive with me.